and share my screen again. Okay, so now we have two equations here, right? So let's look now at what do we do with these things, right? So we've got this RT coming in. We're going to use that kind of simplified version of the correlation receiver where we're multiplying by the symbol, and then we're going to integrate. Now, these symbols have a certain basis or support to them, right? So they're going to be defined over 0 to t, right? So now a simple version of a symbol, we haven't talked about exactly what they look like in a lot of detail. We've given a few examples, but because it gets more complex when we consider some real life constraints. But for example, assume that it's a rectangular pulse from 0 to t. So it has a constant amplitude between time 0 and t. And that could be, in the case of BPSK, it could be plus A and minus A, right? And we saw that as an example in the homework. If you're scaling to higher values, and it could be larger constellations, and it could be 3A and minus 3A, 5A and minus 5A, or it could be 5JA or minus 5JA to make it orthogonal, or it could be 5 plus 5J, or probably there'd be some square root of 2's involved there because, well, it just falls out from Pythagoras there, right? But well, actually, maybe it would be just 5 plus 5J or 5 minus 5J. All these things are multiplied by this kind of basic amplitude scaling coefficient, and then it's defined over this 0 to t. So I kind of hinted, we'll see that sometimes we use different types of symbol shapes to adapt to particular channels, but for this case, just visualize it as a rectangular pulse. So if we're going to integrate this, we're focused on this, receive signal relative to the symbol set that was sent, right? So we're going to integrate that then from 0 to t, right? And then we're going to examine the results at the end of that period, right? So we're going to, this could be an analog form, or it could be sampled and have amplitudes associated with each of those samples for both R and for S. And so that you might have many samples within this pulse period, right? And then, but we're going to integrate that each time. And for each sample coming in, and that's a kind of stepwise integration process, numerical integration, and where your dt is kind of a really small delta t, right? To calculate that error under the curve for each rectangle that's approximating that area under the curve. So then we sample at the end of that time, right? So we can write that as 0 to t RT times S of t, right? So that's looking very interesting, right? So now in a match filter case, we're going to convolve this R with this impulse response of the filter, right? So that's done from 0 to t, right? So it's a causal system. Things don't happen before time started, right? So starts at t's equal to 0, the beginning of time, right? And now we're going to look at the output of this is continuously convolving these input signal with the impulse response of the filter, and at any given time t, we're going to look at the result of that integration, right? So we're going to do this in terms of this tau, and it's going to give us a result that's a function of t, right? We're going to integrate out the tau, and we'll end up with a function of t. So we're going to say, all right, what is this h of t, right? We're going to say that this is a matched filter. What do we mean by that? That is, we're going to set its impulse response equal to the impulse or the time function of the symbol, but we're going to modify it, right? We're going to negate the time, so we're flipping it, right, in time, and we're then offsetting it by this value t. That kind of helps make it realizable, right? So that if we flip it around 0, then we end up with negative stuff. So so we have this period t that we're looking at, and so we're creating this t minus lowercase t. This is what we define as a match filter, and now we can look up here and we see, well, we actually need h of t minus tau, not h of t. So let's substitute this argument in t minus tau every place we see t, right? So where we see t, we're going to replace it with t minus tau. So we'll have t minus tau there. We'll have t minus t minus tau, which is minus t plus tau. Okay? So now let's substitute that back in, and we're still integrating from z out to from 0 out to some arbitrary t. But we've just directly substituted things in here, but realizing that we're going to sample this at a time t, or nt really, but we'll just look at that first period for now. So here we can replace that lowercase t up there with the period, the pulse period, capital T. Now look at these two things, right? So this is at the instant of t equals the period, capital T. You're going to have this result, and here the same thing, at t equals the period, capital T, you end up with this result. Well, it doesn't matter whether this is called tau or t or alpha or omega or whatever. It's the same equation, right? In the integrand, these are essentially dummy variables. So these two equations are exactly the same. But note that it's at this time t. So here's another thing that I found, and I'll provide you the links to this. But the the both receivers for correlation or a match filter receiver give you the same result at the sampling instant t, but are different elsewhere, right? So let's look at this. Here we have a rectangular pulse that's at plus or minus a normalized to the length of the pulse. Here he's used L. Different person writing this example, but this would be the pulse period, capital T, that we had before. Here, this is the T, or the length of your symbol, and this is the sampling interval, right? So for each of these symbols, we're sampling that receive vector a number of times, right? In this case, it happens to be 4, but could be many more than that. But that depends on the structure of your shape and how important that is. So you satisfy Shannon-Nyquist sampling criteria. All right, so now what happens if we do a match filter? Here, this is our filter response, right? So we see that it's in the case of a rectangular pulse, it's kind of boring. We've flipped it in time and we've shifted it, but it looks the same. That's pretty common, actually, because even some of the more exotic filter shapes we tend to make them symmetrical. So they end up looking the same, but understand that technically we have taken these this particular symbol, and time reversed it and shifted it according to this equation right here. All right, so now let's convolve these two things. Well, we can convolve them graphically, and you'll know that when you slide two rectangles against each other, that when they first start to overlap, there's just a tiny result. When they're fully overlapped, we get the maximum. And as they continue sliding in this convolution process, you get less overlap. And so you get a smaller value, right? When the symbol is negative in this case, and we're convolving it with this match filter, we're going to get a negative going slope that goes down to the maximum when there's fully overlapped. And then as it starts to slide away, then we trend back to 0. And on this next pulse, you see that we're overlapping positive values. So we're going to reach a maximum there, right? When the symbols are overlapping. So the correlator output is different, okay? Because what we're doing is we are always processing from this 0 to t, and so we're it's a little bit different from this in the match filter, where we're starting from 0 absolute and always integrating, always convolving, right? Here, what we're going to do is a process we call integrate and dump. So we're going to integrate only over this pulse period. Then we're going to reset the system. We need extra circuitry to do that. When you're software defined, it's pretty easy. You just reinitialize your variable, summation variable, to 0, right? But we call that integrate and dump type of system. So we integrate, and then we dump to 0, and we start there again, and we integrate, and so on. So we see here at these decision times, right? This level of sampling, we sample the outputs and they are the same at each of these locations, depending upon regardless of whether it's a match filter or correlator type receiver. But in between time, they look very different, right? So so in this case, if you were implementing this in analog circuitry or digital logic gates, let's say, then you would need to be resetting the you would need a circuitry that resets the summation result to 0 at each time, whereas this is just continuously integrating. And you need one of these for each of the types of symbols that you have. But in reality, you see here that we have 2 different symbols, but we can really use one correlator or one filter and interpret the results accordingly by symmetry, right? So if our symbol here is plus a divided by the root of L, this one's minus a divided by root of L, then we see that the shapes of these things are the same. So we can use that same filter and just look at this decision point. So when we look at like this other system here, we've got all these different symbols that we're inputting. This is the most generalized form of these receivers, and it in practice isn't that complicated. And in fact, this one, to be generalized, you would need a different filter for every single symbol shape that you have. Just noting that sorry, trying to switch to the right presentation here. So but we see that typically there's enough commonality that we can just interpret the results here using the same match filter or the signal that we're correlating with, so we really don't have to at once. So let's see, anything else? All right, so that's actually all I had prepared. So I think we ended a little bit early today. Where is my Zoom? And I will okay, I think I managed to stop sharing. Can you see my face?
Yep.
Okay. Okay. Any questions, first of all? Okay. So we will have today is Tuesday, and we'll have another lecture on Friday. Within a day or two, I will release the preview of the exam. May not go into as much detail this time because now you have a understanding of how I give exams and what I ask for and that type of thing. But I'll still give you a little bit of idea of what you'll be held accountable for. You'll notice in these last couple of lectures, we've talked a lot about concepts and not a lot about problems and stuff, actually working through these. And even in your homework assignment, it's kind of looking back at some of our previous lectures rather than the current lectures. So, but I still try to test you on your understanding of these concepts. So, again, I encourage you, if you need it, to join my office hours that I normally have on, I think, Mondays and Wednesdays. If those times don't absolutely work for anyone, like you all have the same class at that time, then let me know. Today's actually my last day at work, my regular work.
Congratulations.
Thanks. So
Congrats.
I'm actually retiring today. So
You made it.
yeah, except I'm still working for Manhattan College. Oh well. But this is fun. So yeah, so I should be, you know, a little bit more flexible. And if you're flexible with me, I'll be flexible with you. And so just let me know. Give me enough time to prepare, and I can help go over these type of things. So the test will look back a little bit, and like one question I'm going to ask you about is Shannon's capacity theorem, and a lot of us did not really fully recognize all the terms in that equation, right? In particular, the bandwidth relationship. So I'll test again on that one, and I'll probably, you know, ask you what is the bandwidth required given the signal to noise ratio to achieve a certain capacity or something like that. So that should be quite easy, right? But you got to know it. If you do know it, then it's easy. But if you don't know it, then it's kind of hopeless. It's one of those type of things. So and we'll try to do some more of the simple or kind of basic probability error calculations that result in these Q functions or something like that. So the homework hopefully will emphasize that. All right, any other questions? Otherwise, I'll give you 14 minutes back to your day.
Right on. I think we're good here, Professor. Thank you very much.
All right, take care.
Thank you.